I'm happy, so sort of surprised that so many people want to hear about the foundations of quantum mechanics. As I said in the email, I'm not sure it's useful for everyone. Maybe it's good to, maybe it will help you sleep at night or feel better about yourself. It's not really going to help you do new calculations, probably. How is it going to work? I think today we do around maybe probably a bit less than an hour and a half, then we stop. We can discuss how long, maybe 20 minutes, something like that, and then we start again. Maybe again an hour 30 or so, and then we'll do another block next Thursday. So it will be on the original Thursday, unless I have a problem with rooms, but I think that should be fine. Okay, so now I can start for real. And let me start right away by something that I think motivates the need for foundations. And to me, what motivates foundation is sentences like this. We know that the moon is demonstrably, it's strong, it's demonstrably not there when nobody looks. I'm not going to write much, but this is what I want to write. And maybe you know who said that. It's sort of tongue-in-cheek, but not fully, okay? He kind of means it. So that's not the crackpots who write me emails regularly, or they could write similar stuff. But it's David Mermin. So a very respectable physicist. Actually, we're going to use later his understanding of Bell's theorem, which I think is very good. But here, I think we all agree, or at least we are all suspicious, that this is bullshit. And there are lots of statements about quantum mechanics that we hear here and there. It's hard to, what comes now are not exact quotes, but the type of stuff people say. Like reality, usually independent of the observer, is impossible. Or quantum mechanics implies fundamental indeterminacy. Or quantum mechanics implies infinitely many parallel worlds. Or usually sentences a bit confusing, like that starts like reality doesn't exist because blah 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 Bell theorem. Okay, so probably you've heard various versions, or it requires a profound change in the way we do science. It requires a profound metamorphosis of our understanding of nature. And I think usually when people say that, people who say such statements are either complete crackpots or respectable physicists. And you cannot know actually who says it usually if you don't know. And the gurus and the crackpots say things that are really not so different from professional physicists. And so if you want to fight this, you need to have a clear mind, okay? Is it really implied by the formalism? What is the formalism forcing us to accept about the world? What is a consequence? What is something you can believe that is not falsified by the formalism? Okay, these are things that I think for a professional physicist are good to know. Okay, and imagine, I think what's good to have in mind is soon you're going to have Christmas dinner in your family, probably. And maybe imagine the situation. Your niece maybe is going to ask, actually, how are atoms like? Something like that, And then, like all quantum physicists, you're going to be embarrassed. Okay? You're going to, of course, if you follow textbook quantum mechanics, you're going to tell her, just shut up and calculate. Or that's kind of rude. Or you're going to say, actually it's a wrong question what atoms are reality. What you should ask is, if I observe an atom in a certain way, and already you don't even believe in what you're saying, okay? I mean, you know there is sort of a notion of stuff out there, and this, yeah, you start to feel embarrassed. So you're going to start to use some metaphors, probably. Okay, you're going to say, you know, like the atom is kind of, the electron is kind of delocalized, but actually sometimes it sharpens its position around a point, and it's like both a wave and a particle. And then you're going to feel good about yourself by saying, but you know, it's just a metaphor. Actually, the reality is a bit more subtle than that. But actually, if you face it, you don't know what the more subtle thing is. Okay? What would you say that is better? Okay? If you know well what you would say that is better, what are the various options about how the world can be that are compatible with this, then probably you don't need to be here. But I think most of us, at least at some point, have been embarrassed by this. And so we have all our kind of intuition in our mind of how quantum mechanics works, but it's based on interpretation, okay, even if they are not formal interpretation. And the problem with our kind of metaphorical interpretations is that they are usually wildly inconsistent. Okay, so they made polls with professional physicists, asking them, okay, I mean, you're not a philosopher, you're not doing this type of bullshit interpretation stuff, but in this type of situation, what do you think happens really in the world? And you ask various questions like that, and I think 80% of physicists or so have wildly inconsistent views that are disproved by known theorems. Okay? And so if we're going to do interpretations anyway, we better do it well. Okay? It's not an extra cost, and I think no one is really a pure instrumentalist telling your niece to just shut up and calculate. Okay, so let's do it better. So the benefits, I wrote a few. You can answer your niece at Christmas. You can fight the bullshit, okay, when there is such bullshit. And you know, you kind of feel it's wrong, but you don't exactly know why it's wrong. And ultimately, you can remove, the ultimate goal, at least for me, is to remove from the theory what Bell called romanticism. And for Bell, romanticism, I'm sorry, I'm going to quote a lot of Bell. That's the issue with all these lectures on foundations. You end up talking of Bell as if he was a god, but he was right very early. Okay, so you want to remove romanticism from the theory, which is all the weird and surprising stuff that we put ourselves, and that is not genuinely forced upon us by what we measured, what we saw in the world. Okay, and some of these things are typical romanticism, things that are not shown by experiments or by even what we know of the theory. Okay. Yeah, feel free to disagree or you know, burst in anger at what I just said. That should be fairly consensual so far. So let me just say, I don't want to spend forever doing introductions of introductions, so I just do a very quick outline. So first, I want to talk about the formalism. And the measurement problem, which is the reason why we are so weird about the formalism. So I'll try to sharpen it. I'm not sure that what I'm going to do is maybe too trivial, because I really want to sharpen while we are unhappy. And maybe you're still not going to feel that there is a problem, in which case you're free to do something else next time during the lecture. Then I think I'll spend quite a long time to talk about Bell's theorem. Try to present it in a sort of game theoretic way that's unusual and that hopefully saves us from all the bullshit interpretation of Bell's theorem. Many things that people say, that it implies that local realism or locality plus realism is impossible, blah, blah. All that is sort of incorrect in a subtle way. And then I'm going to talk about some ways to make sense of the formalism. These are explicit interpretations that we can dislike, that in a way I dislike, but that are examples of sharp theories that answer all the questions. Maybe the answer is ugly, but they answer all the questions. They don't shy away from any question. And the first, I think the easiest for us to understand, I mean, for this crowd, is collapse models. Maybe in some previous talks I talk a little bit about it. And then 4, I'll talk about Bohmian mechanics, which is not a perfect interpretation, but a wrongly hated one. Usually hated for wrong reasons. And finally, okay, if I have time, perhaps 5, the more exotic stuff, like you have like, there is a book by Frank Laloé called Do We Understand Quantum Mechanics that lists all the interpretations. And I could mention a few at the end. But OK, my objective is not really to do the zoo of interpretation, but more try to give us a clear mind about what are the various choices and why, especially these two ones made the choices they made. OK. OK. OK, so I start with the formalism and the measurement problem. OK, so OK, this is going to be very introductory, but I want. So this is, if you like, 1, the postulates. There are a million ways to give the postulates of quantum mechanics. So I start by the abstract ones. Okay, so for some of you, like this is a bit trivial, and hopefully, little by little, it gets less trivial. So there are essentially 3 postulates, OK? The first is the state of the system is a vector in a Hilbert space. Actually, OK, every time I'm going to be more precise orally, it's not a vector, it's an array. OK? You don't care about the phase, the global phase. Dynamics is generated by H. That's self-adjoint. And you have OK, sorry, I will. So very intuitively, the first postulate tells you, well, we'll see it's more complicated than that, but what's out there. Then it tells you how the stuff out there moves, okay, at least superficially. And then you have measurement. And that's a bit the extra surprise. What is it doing here? So what you measure are orthogonal projectors. Pj. And you get the Born rule, which says that the probability of having result j is psi pj psi. And then you have collapse that say that post-measurement you are in okay. So measurement postulate has these two parts. So these are the postulates in super abstract form. Usually, you probably know generalizations of this. So just a few remarks that, in fact, this is already the most general. So you can consider measuring self-adjoint operators instead of projectors. But it's the same, because if you measure a self-adjoint operator, then this guy can be written sum over j lambda j pj. And so it's like measuring orthogonal projectors, except you call the measurement result lambda j. But since these eigenvalues have no meaning, it could, instead of real numbers, it could be blue, red, or ABC. I think it's cleaner to not put self-adjoint operators in the definition. There are also POVMs, okay, that you are familiar with, like generalizations of this type of measurement, but they can be obtained from these postulates on a larger H. On a larger Hilbert space. Some of you also use continuous measurement. Likewise, continuous measurement are included, in fact, logically at least. Continuous measurements are also included. So you can reproduce continuous measurement by taking a Hilbert space sufficiently large, actually infinitely large, and use this type of formulation for measurement. So in the abstract form, we don't need more. If you look at most books, surprisingly, okay, maybe modern and technical books do list these three postulates, which I think are natural. Most books cite usually between 5 and 7 postulates, which are weird combinations of this, plus some old-fashioned extras that I find annoying. So let me that. The first is the superposition principle. If you like, they are historical. Does everyone know what the superposition principle is? Okay, so if you have psi1 of t that is acceptable in the sense that it verifies the dynamics, it verifies the prescribed dynamics with H, psi2 of t that's also acceptable, then this implies that alpha psi1 of t plus beta psi2 of t also acceptable, is also fine. Not only is it also fine, but it happens. Just it's not a principle; it's a consequence, okay, of these. It's just a natural consequence of the fact that dynamics is linear. So we don't need it. Okay, back in the days they needed it because they worked there the other way, but many times these postulates are also included. I honestly don't get why. There is a correspondence principle. And this is used to relate classical observable quantities to self-adjoint operators. And in a way, this is used ultimately that you take classical physics, a classical theory, and it gives you a quantum one. Okay? And this was the hope in the early days that you could always do that. But logically, it doesn't make much sense. Like, it has to be only a recipe. It cannot be better than a recipe, because certainly you cannot usually derive a deeper theory from its approximation. This arrow actually is not. There are many, many quantum theories that give the same classical theory. It turns out, in our case, we are using a lot this type of principles as recipes, and it works well because we are lucky that the classical theories we work with are not ambiguous as far as quantization is concerned. But that doesn't have to be the case. And I think the logic goes the other way. The world is quantum, and classical physics come as a limit, hopefully. And it's not really a principle of quantum mechanics. It's a recipe that sometimes helps guess the form of quantum mechanical models. And the worse principle, not worse, but in the sense that I don't think it's fundamental, is complementarity. So complementarity is really a concept of Bohr. If you are, there is a weak form of complementarity, which is that sort of, I write the weak form, which is that if A, B different from 0. I mean, in general, you cannot measure them jointly. But again, this is a consequence of what we wrote. And there is a stronger version that is due to Bohr, that is seen as sort of a philosophical thing. All the things in nature come in with two faces, like wave-particle duality, okay. And in this stronger version, it's just a bit meaningless, okay? It's a bit Bohrian bullshit from the early days. Okay, so we don't need more than our 3 extra postulates to make sense, and these are historical artifacts. So far, there is nothing to interpret in this formalism. Why is it too early to start our work of interpretation? Because it's fully abstract, it's fully general. It can be instantiated in a million ways, and there is nothing to be done at this level. I think that sometimes a mistake people do is try to interpret quantum mechanics, make sense out of it at this abstract, almost quantum information level. Here, there is nothing to interpret. To interpret something or understand what it means, you have to have a theory of the world. And that means instantiating both the Hilbert space and the Hamiltonian for what the world is made of. Okay?
And Alfred,
yeah.
you put so the fact that two particles live in a tensor product over space, you do not put as a...
No, I would not put that as an extra postulate. It still fits. It turns out you have to guess how we construct Hilbert spaces, and it happens that our Hilbert spaces have tensor product structure, but
it's more of a recipe for you than
I would put that in a recipe, or then empirical experiments gave us the info that this is a good choice of Hilbert space, but and they are not even quite tensor products. When you look at fermions, actually they are anti-symmetric Fock spaces. I mean, this is just, I don't know. I don't think that's needed, at least. I agree. I put that more in recipes. OK, so I will do several instantiations of the formalism to give examples of what I mean by instantiation. So the first instance is like the single particle case. In that case, the state is a vector in L2 of R3. Okay, the mathematically minded people will notice later that it's not quite L2 of R3, but something I will keep on saying is that most of the foundational problems are unrelated to mathematical subtleties of are things well defined or not. So I will be a bit careless. And in coordinates, it's the things that the wave function that to x associate psi of x. Certain choice of coordinates. The dynamics is the Schrödinger equation, so it's IH bar d over dt psi t of x. Laplacian, so you have a first kinetic term. So OK, it's just some weird heat equation. And then the measurements you do are position measurements, usually, OK. So you take projectors R, where this is a region of space. And you have Bornhole is now that the probability to measure in the region R is just as advertised, which in wave function representation is this. Okay, this is not the real numbers. This is really a region. And the collapse is that post-measurement psi of x goes to sort of 1 over, it's projected in this interval, psi of x. So these are the early postulates, the one you see in the very first courses of quantum mechanics. Okay, some technicalities that I won't write. It's not quite L2 over 3 if you want to be fancy, because we are taking carelessly second derivatives. But being careful about the function spaces doesn't bring any conceptual understanding. So you do what you want, but I don't care. Other point is that I'm taking a position in finite regions of space, because if I take sharp positions, the Born rule is still defined. Okay, like psi of x gives the absolute value of pi square, gives the probability density, but the post-measurement state is ill-defined because it's the root of a Dirac delta. So it's not even a distribution, it's the root of a distribution. And so you have to, that's introducing a needless problem. Okay? So there is usually, so it depends how this was introduced to you, but there are usually fancy derivations of this, of the why is it the case. So there is a fancy derivation that I think is unconvincing, and that is based on these old-fashioned postulates. So you start from the classical H, so the classical Hamiltonian, mechanical energy essentially. Then you use the correspondence principle to put ats. And you turn these into operators. Then you use complementarity arguments to say that x and p are complementary, so they have this commutation relation. This is purely algebraic. So far, it's a purely algebraic exercise. You don't even know what they act on. And then you use the Stone-von Neumann theorem to do, then you have to do representation theory, know how the operators act. And this is the Stone-von Neumann theorem. Implies that the Hilbert space, okay, up to isomorphism, up to tensor products with whatever else, is L2 of R, and that x psi of x is equal to x psi of x is x psi of x, and p psi of x is minus I h bar dx psi of x. I think this derivation doesn't prove much because it's using principles that are at least as weird and peculiar as the equation we are proving at the end. And in my opinion, so this is not a very good justification. And the good one, the better one, is more disappointing. It works empirically. And in particular, there is a difficult story that's not a purely mathematical story like this, of how this quantum mechanical equation gives classical physics as we know it in some limit. And this is tricky. I mean, this line is tricky because there is this whole decoherence story and the measurement problem in between. So this is tricky, but this is what would constitute a correct justification of this equation, in my opinion. And sorry, I shouldn't have. There is a problem. So now we could do foundations for this. Like in the early days, people tried to make sense of this wave equation for a single particle. And when you look at it, so it was originally matrix mechanics was invented just a year before wave mechanics. So they had the abstract algebraic formulation before they had, just a tiny bit before they had the wave function, the paper of Schrödinger with the Schrödinger equation. And Schrödinger basically initially thought, okay, I've solved the stuff. Like now, instead, now we have a simple understanding of the world made of extended objects. Beforehand, points were punctual, and now they are a little bit spread in space. And this is much nicer. He thought really he had so under the formalism. That was very, very short-lived, okay? Like very quickly, Heisenberg himself understood that there was no trivial physical interpretation of psi of x. One of the problems is, of course, the bound rule, that the way we relate the wave function to our predictions is via this peculiar rule. But this is not the only thing that is very subtle, I think, is that the most important thing, apart from the bound rule, is that there is a coincidence in the one particle case, which is that the physical space is equal to the configuration space. So the wave function is a field in space. This is a coincidence. This is just for single particles. This disappears. And so even if we didn't have the problem with the bound rule, the interpretation of a psi in configuration space would be much weirder. You couldn't really naively see it as a field. Okay? And so there is no good way, in my opinion, of trying to make sense of quantum mechanics by working with single particle quantum mechanics. Okay, like there is no. It's too simple and it evades many of the no-go theorems actually. Okay, so what would be the best instantiation? Actually, if we're going to do foundations about the world, we could as well look at the true instance, or what is believed to be the true instant, which is the standard model. So usually in all experiments, most people here, we are used to having some effective Hilbert space and some effective Hamiltonian that are designed. Okay. Both the Hilbert space and the Hamiltonian on it are things we fabricate. They are things we build in the lab usually, that we design. But deep down, there is in fact only one Hamiltonian. There is no freedom. Only one Hilbert space, at least at the deepest level. It's not something that we can choose. Okay, like there is a certain Hamiltonian. If we were to be arbitrarily precise, arbitrarily fine-grained. And this deepest description right now, after decades of experiments in colliders, is believed to be the standard model of particle physics. And so in the standard model, of course, it's a very complicated model. But effectively, we have a certain Hilbert space that is a huge tensor product over all possible elementary particles of some Fock spaces associated to each particle. It's a colossally large Hilbert space, but people believe, at least, that we know a good approximation to the fundamental one. And the Hamiltonian is harder to write down, but it's some type of kinetic term plus local interactions between these particles. Okay. Technically, the standard model is an instance of a quantum field theory, which itself are particular quantum theories. So all the original abstract formalism is still valid for the deepest description. There is no new stuff when you go to quantum field theory. Even though people use very different tools like path integrals, the scattering matrices and stuff, this is still the same quantum mechanics. There is still a Hamiltonian, there is still a state space. All that stuff can be recovered. Therefore, those who are, this should be understood as like this, because perhaps for those who are mathematically minded, this is forbidden by Hack's theorem. But okay, at the heuristic level at which we understand the standard model, this is what we have in mind, that there is a large tensor product associated to all the fundamental particles Each of these is a Fock space.
But you say so spin, for example?
Yeah, there is spin.
Oh,
you're right. Yeah, this is more complicated. But the fact that I say it's not exactly equal is not so much because I'm discounting spin, that because there are theorems that once you turn on interactions, this Hilbert space is not so well defined. But okay, let's say we put a very small lattice spacing in the universe, this disappears, we are happy.
Okay, I had a question along the same lines. Like when you say particles, it's like you can just a number of degrees of freedom, right? Or it's,
I'm really thinking fundamental particles. Then you can have many of these fundamental particles by having higher Fock states in the Fock space.
How should I understand a fundamental particle? Is it like a degree of freedom that can carry information, or like
at this stage, think of it as something that has a creation operator in all points of space. That's not quite true, but I think that's good enough for it.
And then there is a well-defined number of those, and you can use
at least it's believed right now that okay, unless there is more stuff that hasn't been found, that each part is known.
But when you have like a field theory, for instance.
So this is fine in field theory, okay? Like the Hilbert space of a scalar field theory is Fock of L2 of R3. Okay, so this is always, you can go from the number basis to the quadrature basis in a way. So the number basis is the particle basis, and the field basis is the quadrature basis. The particles are not conserved. Okay, basically this interaction term here, couple different particle number sectors, and this is why the field theory description is more natural. But yeah, so a field theory, if you see it a la Weinberg, is a theory of particles, okay, just not conserved in numbers. In a way, I don't care so much. Okay, my whole point is that there is a fundamental Hilbert space in principle. I won't say more about it, actually. I just want to say that this is not a different game. This is still the same game we are playing. It still fits within this formalism. And in principle, if you want to be super rigorous, that's sort of what you should deal with if you want to make sense of the world, because the world is made of these fundamental particles of the standard model, or of these fundamental states. Okay, but there are, of course, problems, so it doesn't, I just maybe say it orally. As you know, there are some limitations to this understanding we have. There are huge technical difficulties, first, in making any computation. The standard model also doesn't have a continuum limit that's well defined. Okay, so there is necessarily a cutoff. Okay. There is one part, the strong force sector, in principle, has a well-defined continuum limit, but proving it is a millennium problem. But the rest is really believed to not have a continuum limit. So it's not final. That's our deepest description, but cannot be final. Other reason why it's not final is that it doesn't have gravity, quantum or not. Still, in a way, logically, it's a success of reductionism that we managed to do this. And so it's important to remember that reductionism, at least logically, still works in our world. We have never seen top-down causation of weird types. Always the big stuff emerges from the small stuff. That doesn't mean it's the right way to deal with physics methodologically. Okay, often this is a terrible idea to understand everything from the ground up, but logically the bigger stuff emerges from the smaller stuff, and that's still true. Okay, so what is reasonable and what we should have in mind in foundations is multi-particles. Multi-particle non-relativistic QM. So you have electrodynamics is a subpart of the standard model, and you take some non-relativistic limit. And you get like n particle. And the common view, like if you see almost all of the papers in foundation, they are trying to make sense of this. Okay? It's a sweet spot in terms of hardness, and it seems you already have all the subtleties. So in that case, maybe the state space is just a tensor product n times of L2 of R3, which is just L2 of R3n. Dynamics is always annoying to write, but it's like IH bar dt psi you sum over all the particles the kinetic terms. And then you have an interaction term. I'm thinking electrostatic, but that could be whatever screened electrostatic interaction or even effective interaction. Okay. So in good approximation, we can consider the world is made like that. And I think that's reasonable to interpret, to try to make sense of quantum mechanics this way. I didn't say what are the measurements. You can still think we just do position measurement. So the same as before on individual particles. On individual particles. Okay, that's the sweet spot. So now I'm ready to.
Sorry,
Enough for my.
Yeah. I didn't understand your point on this 1.4 example. What it says? Yeah.
For about point 1 or?
No, just all this multi-particle non-reducible quantum mechanics. What was your point with this?
My point is just that this is not the standard model of particle physics. It's an approximation of the standard model. But it seems all interesting quantum mechanical phenomena appear already in this limit, and all the paradoxes, all the complications appear already. But we have some intuition about that stuff. Whereas the standard model is a huge mess, it's impossible to say anything, and we are stuck in calculations forever. So I think this is the picture we want to have in mind when we're trying to make sense of the theory. And later on, when we construct collapse models or Bohmian mechanics, this is the type of interactions and Hilbert space we have in mind.
Okay.
Yeah.
So is it important to be non-relativistic? Because if you think what is, well, I mean, when we speak about Bell's theorem and possibilities, we use the finite speed of the elements.
But in quantum information, we have a notion of no faster than light signaling that in fact doesn't require, that has no relation with the speed of light.
So introduce this as an additional element.
So you're right. I mean, it's true that especially when we discuss Bell's theorem, we sort of have to split our minds and understand. We are going to say things are space-like separated, even though we are doing some non-relativistic stuff. But the hope is that it doesn't matter so much. Okay. But there is a whole branch of trying to make sense of the relativistic setting, and since it's much harder, okay, we have to forget about it at first, I think. So now this is sort of all the formalism I wanted to do. Sorry, it was a little long. But now I want to say why we are unhappy. Okay, or why is it legitimate to be unhappy? Unless there are questions. So just to say, this is going to be our quantum mechanics. When I say quantum mechanics, I mean this problem. Okay.
Yeah. Is the QED part important, because the conjugate momentum will be different if you have electromagnetic field, or is it just to install?
No, I don't care. I don't even have an electromagnetic field here. It becomes a Coulomb interaction or some short range or either short or longer range interaction. I'm just saying there are interactions between particles. Okay, so why are we unhappy? And probably, and I'm pretty sure you were unhappy at first when you saw that stuff. And then you forget why you were unhappy because you use it a lot. So, but you only got used to it. Okay. And I think the first issue in all of that. So, okay, now I'm moving to 2. Why are we unhappy? And the first point we are unhappy is this measurement thing. And this, I think, is something, this is something Bell and actually Einstein had understood. We have a prescription for dynamics that tells us how things move. But measurement apparatus are actually made of things that move. So in principle, they should be describable by the second postulate. Okay? And it's very weird to introduce in a fundamental theory the notion of measurement, which is an effective thing. Okay? Measurement is something that what can be measured is something you deduce from theory, not an a priori in principle. So I quote Bell in the famous article called Against Measurement. He said, like, Einstein said that it is theory which decides what is observable. I think he was right. Observation is a complicated and theory-laden business. Then that notion should not appear in the formulation of a fundamental theory. I think Bell is right in a way, and that explains partly why we feel weird about measurement being so central. Worse, I think there is also a risk of contradiction. We are using wildly different dynamics to describe measurement, to describe physical systems when there are measurement apparatus and when they are just described quantum mechanically. One is linear deterministic, the other one is nonlinear stochastic. And clearly, we could risk that the predictions are different, okay, depending on what you use for a certain thing. So as we will see, the risk doesn't happen practically because of decoherence, but that's a big concern that we should have. And ultimately, there is an issue of precision. What is a measurement? It's never really explained. How do I know I'm doing a measurement and not something else? To this, the answer, there is this story that there was a case at the Supreme Court, and Supreme Justice Potter Stewart had to define pornography. Okay, and he said, I don't know how to define it, but you know it when you see it. And here, it's a bit the same. Like experimentalists, they know it when they see it, a measurement. Okay, but it's always a bit difficult to define more precisely than that. And the fact that we cannot is a little suspicious. Okay, that's really weird. What would be satisfying, something that would be nice, and that we will try to do a bit later, is if measurement could just be a consequence, if we could derive it from 2. Okay, it would be okay if 2, the dynamics, implies 3. Okay, but here, the fact that we fix the 2 independently is highly suspicious. Okay? There are deep reasons why it doesn't bring us complications. It brings complications, but it doesn't bring contradictions. But I think it's important to have in mind how weird that is, probably how shocked you were when you heard it, and now, okay, you're used to it, but try to remember how unhappy you were about it. The other point, unless there is a question about this measurement stuff, I will say more about it anyway. What is the status of psi in this? The formalism is super vague. So when I had this lecture at Polytechnique, I think Dalibard had a very smart way of saying what the state is. He was saying something, I'm not sure it's exactly what he said, but something of the sort. Everything you can say about the system is in the quantum state. That's very smart because it doesn't say if it's real or not. Okay, like it's compatible with all interpretations. But so there are the two main opinions you can have. Interpretations usually are classified depending on the status they give to the wave function. The first option is psiontic, means the wave function is real. It's a real thing. And there are strong arguments for the wave functions to be real. So let me just list the pros. Well, there are interferences. Okay, like that seems very real, like a real thing happening from the wave function. And there is also the standard model. I mean, the sort of deep down, I know this is not super clear why it's a pro in this, but sort of we have a most fundamental wave function of the universe that evolved with the Hamiltonian of the whole universe. So the wave function is a thing that we can define even at the most fundamental level in principle when there is no observer, no any such thing. So what is it in that case if not real? The opposite option is to be psi-epistemic, and to caricature a bit, it means it's in my head. It's like a probability distribution. Okay? And there are some pros to it, which is that collapse looks like Bayes' rule. Do I have other pros? No, that's the main pro, okay? So when you use postulate 2, you really tend to think of the wave function as something real. And when you lose the measurement postulate, you really see it as something effective, something that's in my mind that I used to make prediction. But of course, I don't believe for a second that it's real. I'm not so naive. And I think, I don't know, who here thinks it's more real? Raise your hand if you think it's more real. Who thinks it's more in their head or like a prediction? Well, it's fairly balanced. I think the point is that you're right. So it's not exclusive. So you could answer that it's mixed, for example, that there are maybe in a way it's not well diagonalized. It contains elements of reality and also elements of our knowledge of reality. That was going to be precisely my point. So it seems that it's a bit of an in-between, you're right, usually. And I have this quote that I have to find, so yeah, that probably you know. This is this quote of James. So I'm not going to write the quote, okay, but it seems to be an omelette of the two. And I think this is a very good, let me read the quote. Our present quantum mechanical formalism is not purely epistemological. It is a peculiar mixture describing in part realities of nature, in part incomplete human information about nature, all scrambled up by Heisenberg and Bohr into an omelette that nobody has seen how to unscramble. And if you look at people in foundations, they tend to disagree immensely about how it should be unscrambled. But they all agree this is what should be done. Okay, we want to understand in our description of nature what is real and what is in our mind. Okay, what is just what is probability and what is things in the world that move. And certainly the way we understand, the way we build our metaphors even after of the real world is strongly influenced by this. Okay. If you think the wave function is just in your mind, I mean nothing ever collapses in nature. Okay. Questions about this? So I think these are the main two things we are unhappy about, this very weird role of measurement, and the fact that it's not clear what quantum mechanics is about. Is it about measurement results? Is psi what quantum mechanics is about, or is psi just a tool? That's quite unclear. Okay, for Copenhagen interpretation, the answer is we don't care. Okay, like just the output are measurement results. This is what it gives. That's enough. Okay. I think it's totally fine to have this position methodologically, but I think very few people believe in it ontologically. Very few people believe this is true, like really there is no outside world. And if there is an outside world, then you can certainly ask, how is it and what is it made of? How does it evolve? Okay, so let me move 3 to decoherence. Decoherence is sort of why it's not so bad, but it's often exaggerated as, and people often say claim that it solves the issue with measurement, and that's not true. So I want to explain it solves part of the issue. It's in a way, simple result. So I apologize for those who are very well aware of that stuff, but I'm hoping some people are not. How does decoherence work? So the idea of decoherence is just to move the Heisenberg cut one step away. You stop applying the measurement postulates to your system. You introduce the measurement apparatus in the description. So now, okay, I do first the standard story. Okay, the standard story is the following. So you take now a larger Hilbert space, that is the Hilbert space of the system, tensor with the Hilbert space of your apparatus, and you build up some Hamiltonian. Okay, that I'm never going to make explicit, but that's the individual Hamiltonians plus some interaction term. Okay, this guy is usually some linear bass of oscillator. It's usually linearly coupled this way. But in principle, you can think of many things. Usually, it's a simple linear system. And then you evolve an initial state with this Hamiltonian. Sorry, this is H dot. There is a T here. And you start from a superposition in your pointer basis, tensor an initial state of the environment. And after this evolution, the state can be written, that's always true, and 0 out plus beta 1 okay. You get a state like that, and that's always true. I didn't have to design my system particularly well to get this. And this is when the hard work starts. You have to look at your model. You make a certain series of approximations. Usually, you do 20 pages of calculations to arrive at a result of the form. So you do calculations for your particular choices of Hamiltonians. Okay, there are dozens of papers that do this type of calculations for certain Hamiltonian, and you get at the end, ta-da, that the two environmental states are orthogonal. Okay, I should say I didn't write it anywhere, that I took the system Hilbert space here to simplify to be C2. And here, it's something huge. Okay. Well, so you work very hard, and you show that this goes to 0, or approximately 0, when t goes to plus infinity. That's where the hard work goes. And often in these papers, people are a bit out of space here, so they go very fast at the end. They define the density matrix, that is the trace over the apparatus degree of freedom of the total state. And in this representation, what you see is that rho was something like that. It had coherences. And after this evolution, you get just this. And you say, now are filled with joy because the coherents are gone, and you say, oh, this object here is exactly like a statistical mixture. So it's as if the system had collapsed in state 0 or 1. And thus, it has collapsed. Okay. But this is certainly not sufficient. Okay. Nothing changed after this line, and this line here is still correct. Okay, the superposition never disappeared here. What happens is here, at the end of the day, at the end of this proof, we are cheating a little bit. We are saying this density matrix is the same as the density matrix I would have obtained in another way. So they are empirically equivalent as far as predictions on the small system are concerned. Hence, they are the same physical situation, but that's not true. Okay, like there is a jump. Two objects can be obtained in different ways. And here, this is here an improper mixture. It's still entangled.
There is a depends on what you call physically doing a partial trace, right? You can give a definition by saying, okay, I give up on all this information in the environment, and refreshing the environment, replacing it by another, and I give up on this environment.
I don't know what mathematically means giving up, but if I do this,
pledging to never measure anything in there.
Yeah, but you see that this. Are you going to prove that things work by assuming such things? This is. Why would I? And then if actually nature or whatever could make a measurement, we could violate by inequalities with the environment, and we could witness this entanglement. We could witness that nothing has collapsed.
But if you don't use your knowledge of the phases to undo the evolution.
Yeah. But the fact, reality doesn't care about your knowledge. Okay, I guess it's.
Let's keep this debate for later.
No, sort of. I'm assuming.
I'm always surprised that people don't define what is actually physically the partial trace, or like isn't there like a possible definition of what is a partial trace?
Physically, no. I mean, just here an informational thing. But again, I think.
And when you work with inverse space, it's normal. Why you have to do partial trace?
I think the question is, how do you interpret physically doing a partial trace? What does it mean? I think it means pledging never to use that information.
And discarding the information.
Discarding the information. But how physically would you discard this information?
Well, it's just like you say everything. The result of my calculation later, if in fact I can use this result, this projective matrix, and it will give me the right results, unless at one point
I understand. In a way, I agree with that. But what you're giving is an operational statement, like you're trying to say why it's not going to bring weird contradictions and stuff. But I'm trying to say, okay, here, it's not a bad word. We are trying to do a bit of metaphysics. Can we really take seriously the fact that we are just given postulate 1 and 2, that's how nature evolves in a way, and then concluding that only one of the two happens? I'm saying no. I'm trying to argue for no. Okay.
But it looks like it's the node of the problem, like this operation is really the one that is going to be problematic.
But in a way, forget about this operation. The final state is this. Okay. Yeah. So I'm just saying that all of this, if you like, is putting the dirt under the carpet. This is important because it ensures that exactly where we put the Heisenberg cut doesn't matter. So this ensures at least that we don't get massive contradiction in the formalism. But certainly, by doing extra operation on this state, we will never prove that only one of the two branches exists. Okay. But certainly, the superposition will remain. It's just a decoherent superposition.
But,
No, but I think you're right in some sense. The problem is not so much the density matrix that you get at the end. The problem is to say that only one of the two, that you will only see one of the two, that this represents a probability distribution, that really you see only one of the two. So getting to this by saying we do a partial trace doesn't solve it, because as you say, you still have both options there.
I agree, but I think that's not what Philippe.
So I don't see the partial trace as such a big problem in the sense you discard part of the atoms, you send them to the other end of the universe. But
still, this is going forward, maybe we will talk about this later, but like in the X complex formalism.
Yeah.
Like, what
I think-
happens is that at one point you need to do a partial trace. You cannot keep track of all the degrees of freedom in the environment, and
That's okay, but okay. Zurich's vision of decoherence naturally leads to be consistent to the many world interpretation. That's fine, but
no, it's not, well, okay, let's discuss.
okay. These are two things, but if you want to just have decoherence and unitary evolution, the consensus, if you want to go beyond a pure operational framework, is that this gives many worlds. Okay, like there is no way to collapse this superposition.
Nobody believes in many worlds except Google, maybe. But,
So it's really not true. So it's actually a pretty large fraction. I don't believe in it, but that's a large fraction of people who, both in foundations and in other fields, like in cosmology, who believe in many worlds. But if you are in a cosmological context, or if you look at the standard model, what you can do with the system or the way you see it is completely irrelevant for the description. And so that's very weird that it's so central, and so they are going to be less convinced by this argument of discarding information. Other questions? Yeah.
I'm not sure to follow up what the debate is about. So what is the problem again?
Okay, the problem is here, if you claim this has proved postulates 3 from 2, you are missing part of there is something wrong in this. Because this is true that we reach this density matrix. It is also true that this density matrix could have been obtained in another way, with a proper mixture, with a real statistical mixture. But that's not how it was obtained. And massaging this doesn't change the fact that the original state is this.
So it doesn't contradict 3, but doesn't prove it. That's what you're saying.
Exactly, it doesn't contradict 3, but if you actually then, but now if I do a subsequent measurement on this, it's going to agree, it's going to be as if I had measured before. You're using 3 in the proof of 3. Okay, so it's not sufficient. It doesn't, so it is a proof of consistency. It proves it's like decoherence proves that the dead and live cat don't interfere, but it doesn't prove that they don't both exist. Okay. And when we go from this representation to this very quickly at the end, I think we turn a proof of a weak result, which is still very useful, into a proof of a strong result, which is not true.
And also in the measurement idea, you had to know something about your environment to distinguish between the two states, right? So it's...
not sure what you mean.
So here you took partial trace, and you're now like tracing out the environment completely.
Yeah.
But in postulate number 3, you've learned something about your environment that allowed you to...
Yeah, this is unconditional.
Right, right. So it's not, it doesn't prove it, it's just not inconsistent with
it's not
postulate 3 where you throw away the answer. Right, it's consistent with postulate 3 where you throw away the answer, that's all it's saying.
Exactly, it's consistent, but certainly no magic is going to remove this. Okay.
Is removing what? I'm sorry, again.
The state of the system is this, at the end.
Right.
Then you can look at all the partial traces and say, oh, this guy looks like something I could have obtained differently. Doesn't change the fact that the state is this, okay? So the state is this, there is still a superposition, they don't disappear. This is going to get entangled with you seeing result 0 and another state of consciousness seeing result 1, and nothing can prevent that.
What is
But
the
this,
superposition if you don't know the phase?
I mean, also the fact that this thing is dynamic, it's changing as well. So the environment is changing.
Yeah, okay, the weights are not changing, that's what I mean. The weights are not changing.
Okay.
Both are evolving, but the weights are not changing. Again, here questions of knowledge are interesting for what we can do empirically and everything, but here, and I'm sorry, this is more metaphysical. We are trying to see, is the cat there or not? We are trying to answer your niece at Christmas. She doesn't care about what she can operationally do. She cannot do anything operationally. So, okay, I mean, maybe, I'm sorry, maybe we have to disagree on this. Actually, I had a sharpened version of this because Okay, so maybe it's gonna, I fear it's gonna start the debate again, but okay, let me take the risk. So the question is, this is what we get from the standard decoherence story, where the evolution is very simple and we can manage the model. But now, can you do better and still get collapse from linear dynamics? Just not with the usual story, no? Is there a way? Is it just a flaw in the standard discussion, or is this general from linear evolution? And so for this, I'm introducing a fictional story, totally fictional. So I was contacted by a prominent theoretical physicist, like a genuine one, like not a crackpot. And he told me that he had solved the measurement problem with a model and everything. No philosophical bullshit. A concrete model of that type, but with chaos, and taking into account the fact that the environment is not initially in a state that we know perfectly well. In fact, we don't exactly know the state of the environment. That's smart. And there is a little bit of chaos, so this type of randomness can turn into all types of weird stuff. So he contacted me just to add, since I seem to know some stuff about foundations, at least the philosophical stuff, give references, pointers to the literature to flesh out a nice archive paper. So I inquired still, how does it work? Because that's that stuff I learned at school that it's not possible. And he said, okay, you start from a state like this, but now your environment in here, it has, in the last digits, it differs in every realization. And the unitary, it's not like this simple, the standard unitaries we usually have in decoherent story. It's really a chaotic unitary, so it tends to amplify like all the differences. And if you run it with slightly different initial conditions, you get this. And you run your code or that is simulating this evolution many times. You change the last digits in this environment in states, the state of the environment, and it gives you either this or this. Prime, if you like, with the right probability, with the Born hole. I think that's something people call, there is actually known physicists who have arguments of that style that they call the flea on Schrödinger's cat. I think it's an argument by Klaus Lanzmann. But it's not Klaus Lanzmann in this fictional story.
Is that true to follow this? Because chaoticity is a classical argument from something.
Yeah, okay. There is a definition of quantum chaos. I agree that it's a classical argument. Okay, maybe wait half a second. This is not possible, okay? So I knew instantly that the code was wrong or something had a problem. Okay? And if you are used to this, you should see it instantly. How do we see that even with complicated unitaries that have chaos or interacting Hamiltonian, full many-body system, and here very complicated states in huge Hilbert spaces, this cannot happen? Well, so this cannot be. And the reason is that you take limiting cases. If indeed this gives the Born hole, then when I start from this, I should always get this. Okay? No probabilities anymore. And when I start from this, my measurement apparatus, even with all its stochasticity, all its deterministic chaos, should also always give me the other one. And then by linearity, it's never going to collapse superposition. Okay? So by linearity, if the evolution is indeed unitary, well, Okay, I'm being a bit sloppy on how I'm writing it at the end, but something like that. Okay, the weights can never disappear. That's just linearity. So in a way, it's independent from the decoherence story. There is no possible way to derive, at least in that strong form, the measurement postulate from unitary dynamics. From that point, there are two solutions within the standard formalism and two solutions out of it. Because this is very often on archive, you have results also of that type, and often you find the flow. Okay, that cannot be.
Why do you not destroy superposition if environment out and environment out prime are orthogonal?
It doesn't matter. I'm not going to get 0 or 1. Okay, maybe they are not orthogonal, I agree. It could be still coherent. It could be even worse. It could be a coherent superposition. But it cannot be just 0 or 1. So even if you relax what we require in standard decoherence models, there is just no way. So see what are the ground classes of options. First, if you change nothing, you have a bit two solutions. Either you keep only two, and then Schrödinger's cat happens. Okay, like there is no, maybe it's not observable, and that leads naturally to the many worlds. So if you use decoherence alone, this is typically what you're going to get. Or you assume that there is a sharp cut. You put 3 by hand. And if you want to be consistent, this is a bit crazy, but if you want to be this cut to be totally independent of any choice, you can do like Wegener and put it at the level of consciousness or something like that. Okay, like you put a cut 3 by hand somewhere.
Have people tried also to say that 3 is included in 2 in the sense that the fundamental equation of motion is not Schrödinger's equation, but 1 like the stochastic master equation?
I will, exactly. So this is if you change nothing.
Okay.
Yeah. And if you allow yourself now to change things, this leads to, if you allow to change stuff, you have two options. You change 2 a little, 2 a little. It's exactly like Zaki said, such that 2 does imply 3. Okay. So that's collapse models. They do this. They make this choice. So either I say a little bit about them today or next time. And last option, you introduce extra degrees of freedom that, okay, this is a bit sloppy the way I say it, of freedom that choose a branch. Okay, and this is de Broglie-Bohm. Okay, this in here, I'm talking only about sort of realist or interpretations where you try to say what happens in the world. There is a completely other class, and maybe Philippe would advocate more for that are purely epistemic, like cubism, or you say, in any case, you don't try to, you make it about knowledge only. So if you make it about knowledge only, that's a whole other question, and that's why I said, in a way, I erased it, but this is a biased introduction to foundations, because what I want to explain how you can make it a theory of things that move, okay, a real theory of the world, and not just a theory of knowledge. Again, because I think that that's not what people care about at Christmas dinner.
It's pretty fancy when you say that you live in a big simulation and where everything is information.
Yeah, but
that has some impact at the
no, this has some impact. This has some impact, but that's what's worse because this is highly romantic and not really motivated by anything. If you say that, you know, like this is much more weirdness than that quantum mechanics forces upon us. You know, so we really have to aim for a description that has as little weirdness as possible, and not extra weirdness we put on top. That's why I'm not a fan, for example, of this first option here, because I think having infinitely many worlds is a huge price to pay for this to make sense. Okay.
Yeah. Will you talk about this implication? Why that first option, keeping only two, will imply this many world interpretation?
I thought it's sort of what I proved here, but
I'm not very, I don't know the ingredients of this many world interpretation.
yeah. So
I don't even know why it's not satisfied.
okay.
Or why it's implied.
It's a bit long story, but okay. Why many world happens from this? If you keep on and interact with a larger and larger environment, these weights are never going to change. So, okay, you're right. In any case, I'm finished for this first block, so that works. I can explain this in 2-3 minutes. Okay, so what happens if you keep on with the unitary evolution? You end up with something like this on 0. Okay, they all evolve, but plus a tensor I read 0, tensor I wrote 0 on archive. Okay, if you add all the degrees of this is the degrees of freedom of the piece of paper on which your archive paper is printed, plus beta. Okay, and the other option. And they will say, of course, you see only one outcome because your state of consciousness are different in the two branches. And you're sort of, the two things exist, and there are two people, one conscious of 0, one conscious of 1, and that's how deterministic outcomes happen. Why I am not a fan? So I will see if I talk about many worlds later, but very quickly, the pros and cons of this. Pros, it doesn't require anything else than just the unitary evolution. It's very mathematically parsimonious. I think that's the only pro, but that's a strong pro. Negative aspects, you need infinitely many worlds, and they need to exist for real. Otherwise, you can find problems in this type of description. So they have to exist, they have to have their own history, otherwise things break down. Defining the branches is not so easy. When we make drawings like this, it's clear, oh, there are two outcomes. But in fact, the stuff is like continuously evolving. What you have is a huge quantum state. How do you decide exactly how you split it? That's not so easy. So in many worlds, people will say the only thing real is the many worlds. The worlds are only effective. They are sort of the way we kind of split the universal wave function. Finally, for another difficulty in many worlds is how do you explain the Born rule? Here there is a higher weight on this superposition maybe than on this one. There are different weights. How do you explain that this happens more in a way than this? Is a branch bigger than the other? Okay, like the problem of recovering the Born rule is one of the big problems in many worlds. And there is an infinite literature on it, how agents living in the many world would use the Born rule to bet on outcome. And okay, this is the modern understanding of many worlds, that betting is the best way to understand it. Okay, my take is that many worlds is something superficially seducing, but when you see the cost, I think it's not worth it. Yeah.
And housing interference included in many worlds?
Interference is because your branches are never fully orthogonal. Sort of. When they start talking to each other a little bit, you get interference.
No, but the idea I have in my mind is like computational quantum computer as an example. I go to a very entangled state, and then I go back to the pure state as an example, or something like that.
Yeah, they're recombined.
So I created many worlds, and then they've collapsed. They've disappeared, or...
Yeah, I guess. But this is, to be fair, this intuition that gave David Dodge, this gave David Dodge the intuition that there was some power to harness. So I don't want to trash it. Certainly, it's a powerful intuition pump. But I think if we're serious about ourselves, do we believe that the difficulties we have with quantum theory imply infinitely many parallel worlds? I think seriously, like, let's say they ask you to come on TV, you know, and say it. I mean, some people do it, but I would feel weird.
It's totally that there is infinitely many. It's like there are infinitely many more at each point in time. Like the thing is
you're right.
constantly growing.
Yeah, it's constantly growing.
It's completely blowing up.
Yeah, it's completely growing up. Yeah, but you have to understand if you stay at the level of the formalism, let's say you're not so fond of purely informational interpretation because you do cosmology of the Big Bang, okay, quantum cosmology of the Big Bang. If you don't want to modify anything, you put Heisenberg cuts, okay, you put measurements, but then this is I don't know if I didn't write it down, I think it's, but there is this quote by Bell, you know, did the wave function wait for humans before jumping or before collapsing, or was it with the first sentient being that it started collapsing? You get this type of weird problem. So people are like in this context of cosmology, like the many world, which at least is completely observer independent, which makes sense in this cosmological context where there were no